Bismillahirrahmanirrahim. Find the Z parameters of the two-port circuit in figure 1. So this is the circuit that we are given and we have to find the Z parameters. So first of all, we must write down the equations that govern the Z parameters. So for the Z parameters, V1 is equal to Z11 I1, and this is V1 and this is I1, right? Then plus Z12 I2, this is I2 here. Note the direction of I1 is this way and I2 is directed in this way, right? And then V2, this is V2 here, the second port. This is usually called the input port and this V2 is called the output port. So at V2 we have Z21 I1 plus Z22 I2, right? So these can be written in the metric form. For example, we can write it down like this: V1 V2 is equal to Z11 Z12 Z21 Z22 I1 I2. So these are our Z parameters: Z11 Z12 Z21 Z22. So there are many ways in which we can find the Z parameters for the given circuit. For example, first note that if we put I2 is equal to 0, let I2 is equal to 0, which means we switch off I2 at this port, and then this becomes V1 is equal to Z11 I1, right? And this means Z11 is equal to V1 divided by I1 when I2 is equal to 0. And here when I2 is equal to 0, V2 is equal to Z21 I1. So that means Z21 is equal to V2 divided by I1 when I2 is equal to 0, and here when I2 is equal to 0. So similarly, if we put I1 is equal to 0, let I1 is equal to 0, right? We switch off I1 here. So in that case, these terms will disappear. So then V1 is equal to Z12 I2, and that means Z12 is equal to V1 divided by I2 while I1 is equal to 0. And in this case, when I1 is equal to 0, right, we have V2 is equal to Z22 I2, and that means Z22 is equal to V2 divided by I2 while I1 is equal to 0. Actually this also defines a way in which we can find all these four parameters: Z11, Z12, Z21 and Z22, right? We can switch off I2 here and then find the two parameters Z11 and Z21, and then we can switch off I1 and we can then find out the other two parameters Z12 and Z22. By switching off I1 and I2, we mean that we turn off any current source here at the port, or we open circuit this port, right? We open this port. When the port is open, there will be no current flowing in here. So that is why these are all four parameters are also called open circuit impedance parameters. Open circuit Z parameters are impedance parameters, right? So for example, Z11 is equal to V1 divided by I1. This is input impedance, open circuit input impedance. Then Z12 is V1 divided by I2. So this is transfer impedance from port 1 to port 2, because this is V1 and divided by I2. The unit is ohm because this is voltage divided by the current. And then we have Z21, so that is V2 divided by I1. So that is all again voltage divided by current. The unit remains the same, impedance, and this is open circuit transfer impedance from port 2 to port 1. And we have then Z22, which is V2 divided by I2, V2 divided by I2, that is output port impedance. So these are the four parameters, and using this way, this method, by turning off a source at one port, we can find the two parameters, and then turning off the source at the other port, current source at the other port, we can find the other two parameters, the remaining two parameters. So this is the standard method. So this is method number 1, standard method. Using this method, we can find the impedance parameters for any given circuit, right? So when we are given a circuit, if there are any time sensitive components like the inductor here, we must first transform it into the frequency domain using the Laplace transform. So for this inductor, 1 Henry inductor, so this will be SL in the Laplace domain, frequency domain. So L is 1 here, so that is S, right? The resistors are insensitive to frequency, so they remain the same in the frequency domain. So we transform this circuit to the frequency domain first. So this becomes, this is V1 and this is current I1 flowing in, this is V2, this is current I2 flowing in here, this was given as 2 ohm, this is given as 3 ohm, and this is transformed to the frequency domain as S. Let's call this fig 2. So if you're using this method, standard method, so we turn off I2 is equal to I2, right? So let's say let I2 is equal to 0. So I2 is equal to 0 means we consider this port to be open circuited, right? And we connect say a voltage source here, V1. We assume that a voltage source V1 is connected here, and this port is open circuited, right? So that I2 is equal to 0. So we can depict this in this figure. Let me redraw the figure, and so that the things are clearer. So for example, we assume that there is a voltage source V1 connected here, that is the current I1 flowing here, this is 2 ohms, this is S, this is 3 ohm, this is current I2 which is equal to 0, and the voltage at these terminals is said to be V2. And let me call this fig 3. Right? So now I2 is equal to 0, and this terminal is open, this port is open, so there is no current flowing in here. So 2 ohm and this inductor S are in series, right? So we can write V1 is equal to S plus 2, these are in series, S plus 2 into I1, right? So in other words, V1 divided by I1 is equal to S plus 2. But V1 divided by I1 is our Z11 when I2 is equal to 0. So this is the parameter Z11, right? And now we can also see that the voltage V2 here is the same as the voltage across this inductor, because there is no current flowing here. If you apply KVL here, then the voltage across this inductor is the same as V2, because the voltage drop across 3 ohm resistor is 0. So we can say that V2 is equal to S multiplied by I1, S multiplied by I1. So that means V2 divided by I1 is equal to S. But V2 divided by I1 when I2 is equal to 0 is Z21. So we have found out two parameters using this circuit. Now to find the remaining two parameters, we put I1 is equal to 0. Let I1. So let me redraw the circuit again. So in this case, we keep the input port open. Right, and this is voltage V1, and I1 is equal to 0, and this is S, this is 2 ohm, 3 ohm, and we assume that there is a voltage source connected here which is V2, and the current flowing in here is I2, right? So let me call this fig 4. So now there is no current flowing through this 2 ohm resistor. So this inductor S and this impedance, this resistance 3 ohm, they are in series now. So all the voltage drop is across these two impedances. So in this case, V2 is equal to S plus 3 into I2. Right, and then we can say V2 divided by I2 is equal to S plus 3. Well, V2 divided by I2 is equal to Z22, right? So this is Z22, and furthermore, if we apply KVL here, right? So then the voltage across this 2 ohm resistance is 0, and this voltage across this inductor is the same as V1. So let me apply the KVL. This is, for example, minus V1 plus 2 I1, right, plus S, right, multiplied by I2. The current flowing in is I2 here, is equal to 0. So I1 is 0, so this term is 0, right? So this means V1 is equal to S I2, because I1 is equal to 0. So we can say V1 divided by I2 is equal to S, but V1 divided by I2 is equal to Z12. So we have determined all the 4 parameters using this our standard method. So let me summarize them, and we write them in matrix form. Z is equal to the first parameter Z11, it was found out to be S plus 2. So this is S plus 2. Then Z12 is found out to be Z12 is found out to be S, right? S. Then Z21 is also S, and Z22 is found out to be S plus 3, right? S plus 3. So one thing to note here is that Z12 is equal to Z21. So when that is the case, the circuit is called reciprocal. The circuit is reciprocal. So this is a general rule. If the circuit is linear and has no dependent sources, then the circuit is reciprocal and impedance parameter Z12 is impedance parameter Z21, right? So what do we mean by reciprocity or by circuit being reciprocal? So one thing that I have described, that it means that the transfer impedances from port 1 to port 2 is equal to the transfer impedance from port 2 to port 1. So practically it means that if we have this, for example, linear network, and we have this port 1 and this port 2, and we connect a voltage source, for example V here, and if we then measure a current flowing through here I, right, and if we use the same circuit, let me call this fig 5, and for the same circuit, if we switch the ports and now connect the voltage source across this port here, the same voltage source, right, V, and then measure the current here I, then the current will be the same as this one, right? Let me call this fig 6. So in a reciprocal network, if we apply a voltage source at port 1 and measure the current here I, then if we use the same voltage source at this port, apply the same voltage source here, and then measure the current here, the output current will be the same. So if we exchange the excitation from port 1 to port 2 or port 2 to the port 1, the response, the measured response should be the same, and the transfer impedances should be the same. So that is what possible only when the transfer impedances are the same, right? So this was one method of finding the Z parameters. So we can find the Z parameters using another way also. So when a circuit comprises of the resistors, inductors and capacitors alone, and there are no dependent sources, then the circuit is reciprocal, and we can express this circuit in a standard form when there are no dependent sources and circuit is linear. Then the Z parameters, can be found using the equivalent T network, can be found using equivalent T network. So the equivalent T network, the given network also is in T form, right? So we can compare it with the T network, the given T network. So this is V1, this is I1, this is V2, and this is I2, right? And this impedance here is Z11 minus Z12, should be equal to Z11 minus Z12. Then this should be Z22 minus Z21, right? And Z12 here, this impedance is equal to Z12, which should be equal to Z21 because the circuit is reciprocal. Let me call this fig 7. So comparing the given circuit with fig 7, right? This figure 7. So this is our given circuit, and we have transformed this to this frequency domain circuit here. So comparing this first let me see this. So Z12 is equal to Z21 is equal to S, right? Z12 is equal to Z21, right here, is equal to S here, right? And then Z11 minus Z12 is equal to impedance of this branch, which is 2 ohms. So this is 2. And then we can find Z11 from here. So Z11 is equal to 2 plus Z12. So Z11 is equal to, so Z12 is equal to S, so that is S plus 2, right? And similarly, we can write, for example, Z22 minus Z21 is equal to the impedance of this branch, which is given as 3 ohms. So this is 3. So it means that Z22 is equal to Z21 plus 3. So Z21 here is S, so that is S plus 3. So we have arrived at the same set of parameters. If you see, Z22 is S plus 3, Z11 is S plus 2, and Z12 and Z21 is equal to S, here. So using this method, the equivalent T-network method, we have found out the parameters to be the same as we found out earlier. So there is yet another method which is quite easy. So what we can do is we can redraw the circuit here and then apply nodal or mesh analysis to arrive at equations which are similar to these equations, and then we can compare the found equations with these equations, and then by comparing the coefficients we can find the Z parameters. So let me demonstrate this by using the KVL method here. So in our given network, let me redraw the circuit. So this is 2 ohm, then we have this is 2 ohm, this is 3 ohm, this is inductor S here in the frequency domain S. So this is V1, this current is I1, the current here is I2. Note the direction of the currents, right? I1 in this way, I2 in this direction, and this is voltage V2. And let me call this fig 8. So we can apply KVL. So we can assume current I1 flowing here in this direction, right? In the same direction as this one, and we can assume current I2 flowing here in this direction. So KVL in loop 1. So loop 1. So that is minus V1 plus 2 I1 plus S I1 plus I2. I1 plus I2, because directions of both the currents are the same. I1 is flowing in this direction from up to down. I2 is flowing also in the same direction from up to down. So that is why this is as S into I1 plus I2, and that is equal to 0. And we can write it down like this: V1 is equal to, so this is S plus 2 I1, right? So S plus 2 I1, and then we can write it S I2. So if we try to write this equation by inspection, we arrive at the same equation. So if we write it by inspection, so this is 2I1. If we write it by inspection, the total impedances in the first loop are S plus 2. So S plus 2 I1. Then the common impedance is S, and the currents in the same direction, the sign is positive, so S I2, right? So let me call this equation number. Let me call this as equation number 1, this as equation number 2, this as 3. In fact, these are the same, right? So 4, and let me call this equation number 5. Now loop 2. So this is minus V2, right, plus S plus 3 I2, right, S plus 3 I2, S plus 3 I2, and the common impedance is S, and I1 is flowing in the same direction, so this is S I1 is equal to 0. So we can rearrange it. V2 is equal to S I1 plus S plus 3 I2. I wrote it by inspection, right? So now we can compare equation 5 and 6 with equation 1 and 2. These are in the same form. So this is V1 is equal to coefficient here I1 plus coefficient here I2. And this again also is in the same form. V1 is equal to coefficient here with I1 plus coefficient here I2, right? So comparing five and 6 with 1 and 2. With 1 and 2, we get Z parameter is equal to, so Z11, Z12, Z21, Z22 is equal to, so Z11 here is S plus 2, right? So this is S plus 2, and then we have Z12S, Z21 is S, and Z22 is S plus 3, right? So this is the same answer that we obtained earlier. So there are 3 methods. There may be some other method also. We can use employ other techniques also to arrive at equation in a similar form and then compare it with these equations and find the Z parameters. But for example, if the circuit is not given in this form, not a T network, not a simple network, then the standard method will always work. This method 1, this standard method. For example, if we have 2 loops here, or there are multiple loads, then the standard method will always work, right? And however, we can still employ some network analysis techniques to arrive at equations in this form to compare them with these equations here and then find out the Z parameters. But as I have stated, this standard method will always work given any circuit. And also in the standard method, note that we use 2 circuits. First we switch off I2, right? Let I2 is equal to 0 and then find 2 parameters, and then we switch off I1 and find the rest of the 2 parameters. So the values that we obtained in this circuit in the first part when I2 is equal to 0 cannot be used in this part here. The value of V2 here cannot be used in this circuit, in the modified circuit here, because here I1 is equal to 0 and I2 is non-zero. So similarly, the values found here, obtained here, cannot be substituted for values in this part of the problem, in this part of the solution. So both these circuits, they are solved independently, and the first part, it gives us 2 parameters when we switch off the current at port 2, and this second part, when we switch off the current at port 1, gives us the rest of the 2 parameters. But let me say it again, the values that we find here, the values of a V1, I1 or V2 or I2, these cannot be substituted in this second part of the solution, where we switch off the other current and find the rest of the 2 parameters. So both the circuits are solved independent of each other. So you should remember that.